You're right. There is no one disconnected.
Oh, is it?
You're on.
Okay, now that's fine. Okay, good morning, good afternoon, and good evening to all. Thank you for joining us today for day 2 of the World Aquaculture webinar. So first, some brief housekeeping matters. First, you can find the schedule and World Aquaculture 2020 exhibitor list on worldwideweb.was.org, which is on the screen in front of you. All pre-recorded videos will be on the webpage for 30 days, and we will have a live Q&A during the. So yesterday we heard about the diversity of different aquaculture systems and the factors that were impacting on this production of food fish and shrimp from Dr. Matthias Howard, who's head of the aquaculture FAO. And Dr. Fashad then shared with us some of the different components and designs in an aquaculture system that can be used to mitigate these issues. So we actually have 2 sessions planned today on diseases in shrimp, and the second session will be on seafood safety. We've had to swap our speakers around, so Dr. Kallaya will be speaking first. And as we know, disease is actually a key concern in all intensive livestock production systems, and there is no exception when it comes to aquaculture. So I would like to briefly introduce our first speaker. Dr. Kallaya Sritunyalucksana is the principal researcher at Biotech NSTDA, and will be speaking on the response to the threat of DIP1 in shrimp aquaculture. Dr. Kallaya's main research interest is in the shrimp pathogen interactions and looking at strategies for the prevention and control of pathogens that cause disease outbreak in the shrimp culture industry. She has a team that's working on a national shrimp genetic improvement for Penaeus monodon as part of a selective breeding program for this Thai indigenous species. Dr. Kallaya is very keen on national and international networks for aquatic animal health surveillance. Her team has been part of a UK-Thai collaboration working on the International Network for Shrimp Health as a communication point for shrimp research. I will now hand the floor to Dr. Kallaya, please.
the oriental prawn, Exopalemon carinicauda, the Australian freshwater crayfish, Shellac quadriculinatus, the less swam crayfish, Procambalus cacii, the white leg shrimp, the Pinus vanami, and also the prawn of genus Macrobacillium, including Macrobacillium nipponensis and Macrobacillium rosenbergii. There are also two species of crab have been reported to be experimentally infected with the DIV1 in the laboratory. The disease caused by DIV1 results in massive mortality accompanied by the growth sign of disease characterized by the hepatopancreatic atrophy with fading color. The infected animal usually has a soft shell with empty stomach and guts. The moribund shrimp sinks to the bottom, and the mortality in the pond can be up to 80%. The growth size of the DIV1 infection is not clear in the peanut shrimp, but in the Macrobacillium rosenbergii, you can see this in the figure here, the white area inside the carapace at the base of the rostrum, which will be clearer shown than in the peanut shrimp. So in the laboratory challenge, it revealed high mortality of Shellac quadriculinatus, the Procambalus cacii, and Lithopenes vanami injected with the DIV1 population. The mortality rate can be seen with 100% or zero survival within 14 to 20 days. On your right-hand side, to determine the root of the DIV1 infection, the challenge routes here was including the immersion challenge, the reverse gavage, and also the per-hours, which are resulted in all 100% mortality in the Pinus vanami. The histopathology signs of the DIV1 infection include this pathognomonic lesion characterized by the presence of unique basophilic cytoplasmic inclusion, which shown here in white, along with this karyolectic and pycnotic nuclei, which shown in black. The target organ of the DIV1 infection is including the hematopoietic tissues, gills, hepatopancreas, periopods, lymphoid organ, and muscle. The nested PCR for the DIV1 infection has been developed using this ATPase primer, and the inventor used them to screen this farm animal. They collect 625 farm animals, including Lithopenes vanami, Pinus chinensis, Macrobacillium rosenbergii, and Macrobacillium japonicus. Oh, I'm sorry, the Pinus japonicus. And it found that within 625 samples tested, 99 of them were found positive, and with different positive rate. For example, as you can see in this table, the highest positive rate was found in the farm Macrobacillium rosenbergii of 50%, whereas the shrimp Pinus vanami and chinensis is about 15%. with the method Q developed in 2017 based on this ATPase gene, we use them to screen our broodstock in a program to establish a breeding stock from wild capture specimen of P. monodon from the Indian Ocean. Our group participated by screening individuals from capture batch for a list of 14 known viral pathogens and parasites by non-destructive PCR methods, while they were being held in a biosecure facility. In April 2018, we detect this DIV1 in one batch. However, to our surprise, all of these ATPase positive samples were grossly normal and show no gross sign of DIV1 infection. Besides, the histology of this shrimp show normal hepatopancreatic tissue and the lymphoid organs. The surprise results come with the in situ hybridization. Usually, the positive reaction of the DIV1 using the DIV dig label probe, showing the positive reaction occur in the connective tissue in the interstitial space between the hepatopancreatic tubules. However, in the wild broodstock with positive PCR for the DIV1, the positive reaction occur not in the cytoplasm but in the nuclei of the tubule matrix cells and cells in the spheroid. So from this work, we show you that the wild captures P. monodon broodstock from Indian Ocean are positive DIV1 by using this ATPase PCR detection. There is no gross sign of DIV1 or no histological lesion in this positive PCR broodstock. However, this curious in situ hybridization signal that found in the nuclei of infected cell is interesting. This suggests the pathogenic difference among these geographical regions. The more research has to be done. We have published this study in the preprint journal bioarchive along with the peer-reviewed journal, so you can look at this study in the bioarchive now. So, in conclusion, for the recommendation, so the surveillance program, the broodstock of post-surgery quarantine and health certification for ID1 are urgently needed in major shrimp-producing countries. And the emergence of the DIV1 should lead to the warning that polyculture of different species of crustacean may bring high risk for high spread of disease, increase of susceptible species, and evolution of the pathogens. The group of Kui in 2018 also reported that the live polychaete is found positive for DIV1. So, the live feed should be checked or decontaminated prior to use. From our result, we show that the wild capture monodon from the Indian Ocean that intend to use as a broodstock in our program were found positive DIV1. So, to warn that this wild capture P. monodon should be subjected to PCR testing for DIV1 before use. However, we would recommend the domesticated stock for P. monodon SPF for DIV1 than the wild capture broodstock. So that's all my presentation. Thank you for your attention.
Thank you, Dr. Kallaya. That was a very interesting presentation on DIP1, and also personally for me, the sharing of finding this virus in polychaetes, which are used in live feed for shrimp, mirrors the findings in other pathogens for shrimp diseases as well. So we're now opening the floor to the Q&A session. If anyone has any questions to ask Dr. Kallaya about our presentation, you can post it on the live event Q&A chat. So that's in the column which should be to your right. Oh, there's a little button at the bottom of your screen or the top of your MS Teams screen, which you can click on to post questions in. So you just give it some time.
So we're waiting a bit. And if there are no new questions, now we will move on with our next speakers.
Or maybe I could, Dr. Kallaya, if I could ask a question. In your second last slide, there was mention about finding a way to remove DIP1 virus from the live polychaetes before feeding it to shrimp. Is there a method that can be used to so-called disinfect these live feeds? Or should live feeds be produced in sterile, clean environment that's free from the disease before they
I'm hearing you not so clear, but I would repeat the question by you asked me about the polychaete, if they got infected with DIV1, how to decontaminate it.
Yes, exactly.
Yeah, okay. So actually, with the other virus that infect the polychaete, you may normally you check them with the PCR, and if the PCR positive, we recommend you to discard it better than use it to feed the shrimp.
Yeah.
Okay.
I see.
Enjoy. Yes, that's it.
Okay. Thank you. So so the recommendation, Dr. Kallaya, would actually be to discard any polychaetes that are found to be infected or carrying this virus. Okay, so we have two questions here, and I will pose the first question to you. The first question is DIV1 a major concern for Penaeus vannamei now?
So far, to what I know, the DIV1 only be reported in China and not from anywhere else. So, can you repeat your question again? I'm sorry.
Oh, the question is DIV1
in vannamei.
Major concern for Penaeus vannamei now?
Yeah, but however, even though it has been reported in China, but we recommend that the other country should start to detect it or check your stock with this DIV1 primer, especially with P1amide and the freshwater pond, the macrobachium, because as you've seen from my presentation, that they are quite a high rate of positive animal be detected in China. So people should be concerned about DIV1 in Penaeus vannamei.
Okay. Thank you, Dr. Kallaya. Maybe we can look at the third question here in on the Q&A screen. So there was actually a question about whether specific primers can be developed for DIV1, and I think this was covered in your presentation.
And I would like to add more that the DIV1 genome sequence has already been published in the public database. So beside the primer designed by the on the ATPase gene, you can also use this genome sequence to design the primer that suits your facility by yourself.
Thank you, Dr. Kallaya. And for the third question, we have a question asking about any known treatment or control strategies for DIV1. Would there be anything a farm can do to treat infected stock or to stop the virus from being introduced to the farm?
Okay, I think it will be the biosecurity approach like the other viruses control to prevent the viral pathogen into the farm. But the major message about the DIV1 that we are concerned now is about the polyculture. You can see that now people culture monoamide with the microbacium, and that can cause the outbreak and the evolution of the pathogen severely. So that is the major recommendation that the people that the farmer that use the polyculture should be aware of that.
I agree, Dr. Kallaya. So when farmers do farm more than one species in the same aquaculture system, they should be testing for example, the microbrachium and also Penaeus venomai for this pathogen. And in addition, they should also be screening any live feeds, like polychaetes that are fed to the shrimp.
Yes, that's correct.
Yeah, so good biosecurity is very important. All shrimp viruses and pathogens. Yeah.
And as also the use of this SPF stock is recommended.
SPF stock. Dr. Kallaya, if you could take one last question that we have here. There's a question about whether DIV1 can be transferred across to all shrimp species. And I know in your presentation earlier you have showed 3 species of shrimp which the virus has been found in. So
yeah, I think there is more Penaeus species has been found to be the PCR positive for the DIV1 more and more. I mean, in several publications, they found more Penaeus species that susceptible for the DIV1. So, for example, like Chinensis. So, I mean, it's possible that this DIV1 can infect many Penaeus species.
Thank you. Thank you very much, Dr. Kallaya. So that we have so much to learn about shrimp pathogens. It seems that every few years there is a new one that is thrown out to us. So, okay, we have one more question in the Q&A, but I think we'll take it in the panel discussion.
We can also do that,
yeah,
if you want.
Maybe we take this last question in the panel discussion later because it's a bit broader about screening for live feeds for certain viruses or diseases. So thank you very much, Dr. Kallaya.
Thank you.
Because you will have to join us for the panel discussion at the end. We will now proceed with a presentation from our second speaker, Dr. Luis Fernando Aranguren Caro, who will be speaking about the microsporidium EHP, Enterocytozoon hepatopenii, and white feces syndrome in shrimp. So in the past 20 years of his work in aquatic animal health, Dr. Aranguren has collaborated with the FAO and OIE on various projects. He has also been a frequent consultant for shrimp farms and feed companies. He has led the importation risk analysis for introducing Penaeus banami and monodon into the Sultanate of Oman, where he also set up a quarantine strategy for import and movement of shrimp. As the biosecurity consultant for the Ministry of Agriculture in the Kingdom of Saudi Arabia, Dr. Aranguren was responsible for setting up a biosecurity strategy for the shrimp industry and diagnostic laboratories. He is the OIE expert for necrotizing hepatopancreatitis or infection with the Hepatobacter peniae. So I will now hand over the floor to Dr. Louise, please.
Good morning, everyone. I'm going to start sharing the screen to show my presentation. Thank you for the invitation to World Aquaculture 2020 Webinar series from the World Aquaculture Society. My name is Fernando Aranguren, and this is the title of my presentation, Interaction of Microsporidium EHP and the White Feces Syndrome in Shrimp Penaeus banami. So in the agenda, I'm going to talk briefly about 4 different aspects about EHP. And then in 3 different scenarios, I'm going to talk about EHP and white feces in Indonesia, India, and the first report in Latin America. So this figure briefly shows how enteric pathogens such as EHP and HPND have caused a decrease in the shrimp production during the last 10 years. So that is the reason everybody is working on this pathogen, especially EHP. Now, regarding the white feces syndrome, several studies has been focused on to study the causative agent of white feces. There are some studies in which Vibrio cholera has been reported as the causative agent. Some other enteric bacteria, as the ones that you can see here, I cannot even pronounce them. Some other research have been focused on the vermiform bodies that resembles gregarines as the causative agents or associated with white feces syndrome. And there are some reports in which they confirm that EHP is not the causative agent of white feces syndrome. So first, I'd like to give what is the definition of white feces syndrome for our study. So basically, for our study, the presence of white or whitish floating fecal strings, as you can see here with the green arrows, on the surface on the grout pond, along with the presence of shrimp displaying whitish discoloration of the GI tract, and sometimes associated with some soft shell in the animals, is what we consider the white feces syndrome for this study. Now, EHP is one of the most important pathogens in the shrimp industry worldwide, and it has been reported since 2003-2004, first in Penaeus monodon, later on in Penaeus banami. Basically, the target organ is the hepatopancreas, where as soon as they start causing severe infection, it damages the ability of the hepatopancreas to gain nutrition from feed. It causes slow growth, high size variability. Usually, in the later stages of the disease, it has been associated with vibrios. We already know that Vibrio are opportunistic pathogens. In some severe cases, this disease can cause chronic mortalities in shrimp farming. Here we have a typical picture of animal displaying EHP. You can see the typical pale discoloration of hepatopancreas that is also typically for any other enteric pathogens such as NHP and AHP&D. To have as a comparison, we have a healthy section of hepatopancreas, and here we have a hepatopancreas affected by EHP. We can see here the plasmodium stage and also the spore stage. The geographical distribution of EHP, here you can see the red circles. So basically are Southeast Asian countries where EHP has been reported. Pretty much most of the important shrimp farmers project under the WA2020 project. So basically, we decided to have the first approach to the white feces. So basically, as you can see here, we are collecting the whitish GI tract, gastrointestinal tract of white color. And then we also took samples of animals for histopathology and PCR. In all the animals in which white feces were displaying the animals, the GI tract with a typical whitish discoloration, we were able to confirm the presence of EHP by histopathology and PCR. Also, we took samples of the fecal strains. We did paraffin blocks with the fecal strains, and we did histopathology, and later on we did in situ hybridization. Again, all the samples of fecal stream for EHP. Not only EHP was found in the animals displaying white feces, we also found secondary vibriosis, basically what is called the septic hepatopancreatic necrosis, usually caused by opportunistic vibrios. The next year, in 2017, we decided to visit some shrimp farms, and we wanted to do a similar study. We took samples from hepatopancreas and the GI tract. In one pond displaying white feces and another pond without displaying white feces. So in this figure, we can see we determined the EHP load by quantitative PCR. The samples of the hepatopancreas of the animals displaying white feces, the EHP load was significantly higher versus animals that didn't display the white feces discoloration of the GI tract. The intestine, like the white intestine versus the normal color intestine, brownish, we also found significant differences. Again, we found animals that display not only EHP, but also they display septic hepatopancreatic necrosis, as it has been reported the previous year. On 2018, we decided to add one more sample. We have 3 different sampling units: healthy pond, ponds displaying the white feces, and pond with history of white feces. And basically is what the farmers have observed in the past, that basically the white feces is a phase of the whole problem, because later on the animals, as they think the animals cured themselves, and they enter to a different phase. It's called the post-white feces. So we decided to take samples again. Here we have a picture of a healthy animal displaying the brownish normal color. Also, we have animals displaying the typical white feces, and animals post white feces. Basically, those animals are the ones that display the soft shell. If you see, you can see here in the figure the difference in the EHP load, and again, the higher amount of EHP was found in animal displaying the white feces syndrome. After of animals with history of white feces, EHP was also observed, as you can see here. It was significantly lower versus the animals that were displaying white feces. So basically at this point, we know that when the animals were displaying white feces, the EHP load was higher, really high. On 2019, we did similar work in India. Basically, we visit 16 farms in the south and Andhra Pradesh farm and in Surat farms. Using the same methodology, we observe the same clinical signs at individual level and at pond level. Basically, the floating focal strings floating on the grow pond, animals displaying white feces, and animals displaying the soft shell. We follow the same procedure. We took samples for histopathology and samples for PCR. We were able to confirm by the two methods the presence of EHP in the white because the WFC affected ponds. So here we have the table because just wanted to compare that basically EHP was found in several environments in high salinities up to 55 and low salinities up to 4 ppt. Also, regardless the stocking density, low stocking density such as 10 pieces per square meter or high stocking density about 80 shrimp per square meter, we found EHP. And it was found also in small animals as 6-7 grams and also in large animals 26-32 grams. Out of the 16 farms analyzed, we found EHP in 15 ponds. So we confirmed the result by histopathology and in situ hybridization. Here we found something interesting. Basically, in the same tubule, we found spores, EHP spores, and also we found some bacteria. These basophilic masses indicate the presence of bacteria. But basically, it's confirming our suspicious that basically the combination of spores first and later on bacteria is what may be associated with the presence of white feces. Now, moving on 2016, on the Western Hemisphere, specifically in Venezuela, as you can see here, this is an important shrimp farmer region. So we saw some of the grow ponds displaying slow growth, size disparity, chronic mortalities, high feed conversion rate, soft shells, and the coefficient of variation higher than 25%. So basically, it's this typical clinical signs at pond level suggests the presence of a chronic infection. So we run all the tests and the animals were only positive for EHP. So here we use two different primers, 18S and the spore ball to confirm the presence of EHP. Also the animals, we saw the plasmodium confirmed by histopathology and by in situ hybridization. Here we can see the positive reaction for EHP. But what is more interesting for us, in 2018, in the same region, the same farms that reported first EHP or EHP-like, 2 years later, we reported the first presence of a white feces. This picture has become famous. It was taken by a colleague of us. So again, we took samples from the animals displaying the white feces, and guess what? We found EHP, severe infection of EHP. Here we have some example of the plasmodium plus the EHP spores present in the affected animals. And this is a typical picture from one of the farms that we analyzed, in which EHP was found. Again, we confirmed by two different methods. We use a qPCR and also the spore wall. The animals were so positive that even the nested PCR in the first step gave us positive results. So basically, in 4 different scenarios, we can see kind of the evolution of EHP white feces. Basically, we start with a healthy population of animal showing the typical brownish color of the GI tract. Later on, we start seeing some yellowish, whitish discoloration of the GI tract. And even later on, we can find the typical white GI tract in the affected animals. And finally, the animals are so weak is when we observe the flaccidus and the soft shell in the affected animals. Now, by histopathology, we started with a healthy population with a healthy hepatopancreas under histopathology, showing the typical R cells, B cells in a normal values. Later on, we start seeing some sloughing of all type of cells, especially B cells and R cells. Later on, this sloughing of the cells continue. You see less abundance of lipid droplets. And later on, basically the animal is not eating anymore. Even there are no healthy cells in which EHP can replicate easily. So that might explain why the qPCR is lower in this population. So at this point, the animal probably is showing the soft shell. At the end, this injured tissue is colonized by heterotrophic bacteria such as Vibrio. We know that Vibrio lives together in close association with shrimp farming. So basically, the animals at the end will end up with a fibrosis. So as a final remarks, we have found that there is a strong association between white feces syndrome and EHP. And also in EHP endemic regions, EHP can explain the clinical manifestation of white feces syndrome. And finally, we have an opportunistic pathogen. The primary pathogen, in this case, EHP, is not the only one that causes white feces, but in our study, in this case, it was the primary pathogen. In association with opportunistic pathogens such as Vibrios, and a possible and identified environmental factor end up with the white feces. And I just want to thank all the team from the Aquaculture Pathology Lab at the University of Arizona. And this is the funding agencies who provide funding for this research. Thank you, and I will be welcome to answer any questions. Thank you very much.
So that was a really interesting presentation from Dr. Luis, showing the history of how this new pathogen EHP came to first be reported and then be detected eventually in the Americas. I especially found the clear photos of clinical signs of infected shrimp and the pathology very fascinating. So because unfortunately Dr. Luis is unable to join us at this time, we will be taking the questions that were directed to him separately by email. So if the participant in the audience who posted the question, Dr. Luis, could share his email address, or her email address, we would be able to follow up with your reply to your question directly with Dr. Luis. So we will now move on to the panel discussion with Dr. Kallaya. And as promised, we did have one question that came from Dr. Kallaya's earlier presentation. So the question is, if we were to look at the history of diseases spread in the polychaete worms, which are the live feeds for shrimp, so some pathogens that have been found in polychaetes include viruses such as white spot syndrome virus. So looking at this, would you recommend that DIV1 be included to the list of pathogens for us to screen polychaete worms for?
Dr. Kallaya.
Dr. Kallaya, you are muted.
Yes, I'm sorry, Dana. Can you ask me again? I'm sorry.
Oh, okay. Okay. Hello. So if it's looking at the history of viral diseases and pathogens that have been found in polychaetes. So as we know, usually we will find a new shrimp virus, and then people start looking at how this virus was introduced, and you're almost assured that if you were to look in the live feed, you will find, oh look, there's that virus there as well, because live feed are the polychaetes are invertebrates, and so they would also be able to carry some of these pathogens into your shrimp farm. And as we know today, most shrimp farms are so secure that you wouldn't be able to sneak anything past the biosecurity. So Looking at your findings with DIP1, would you recommend that this pathogen be screened for in polychaetes?
Yes, yes. From the work of a Chinese group from the Yellow Sea Research Fishery Institute, they show that this polychaete is also positive, the DIV1. But you know, polychaete is has been shown to be positive for several pathogens for shrimp, such as APEN, the Vibrio parahemolyticus, the EHP, that enterocytosine hepatopenii, and now with the DIV1. So it's very much recommend that when you want to use this polychaete, you have to be assured that they are checked carefully, that they are free of the shrimp pathogens, and also, if it's possible, in the EHP work, we even recommend the farmer to freeze the polychaete before use, because in that case you will kill the EHP, and you know, by freezing with other virus, I guess that it will be killed too. And at the bottom line, it's possible the specific pathogen-free program for the polychaete should be established, and we recommend to use them.
Are there, Dr. Kallaya, if I may add on to this question, are there any SPF stocks of polychaetes available?
Yes, there are. Yes,
Okay.
there.
Okay,
In our broodstock breeding program in Thailand, we also use the SPF polychaete.
okay. So it's not a new business opportunity there. I
No.
thought it might be something people will be interested to get into. So, okay. We have a couple more questions here, but it looks, I'm just scanning through the box on the right, and maybe we can look at this question, Dr. Kallaya, if you feel it's a question about the management of infected shrimp stocks. So if you had a farm that was infected with EHP, white feces syndrome, and DIV1, or any mix of these pathogens, what would you recommend with the management of the infected stocks? Would monoglycerides and probiotics help?
I'm now looking at the live event Q&A.
Yeah.
So is this the question from
Anonymous?
Anonymous?
Yeah.
So which one is that now? There's so many questions here.
If you go to the two last
the
questions.
Second last one. Yes. The question is, can we get recommendation on the management of infected cultured species with EHP, WFS, and DIV1?
Okay. So for me, I will talk about this DIV1 and let Luis talk about this EHP and white feces. So can we get recommendation on the management of infected cultural species with infected DIV1?
Yes.
Actually, I'm not sure if I understand the question. However, I think that first of all, like I said, the broodstock has to be the SPF. We recommend to use this DIV1 specific free broodstock. And also, if you want to stock the PL in the pond, then you have to check, make sure that they are DIV1 negative by using this ATPS primer that we recommend. And be careful of the live feed and the polycultures, as I said in my presentation. And the second question I cannot answer because we haven't do any work about it. Does monoclonal probiotics help? Since the DIV1 is a new emerging disease, we just got the report from China. So we don't have it in Thailand by now. So we don't test this compound on the DIV1 infected shrimp so far. Okay, that is what I can say.
Okay. I think Dr. Kallaya, thank you very much for your answer to that question. I think for the second part of the question, which is about whether disease is this treatable with probiotics and antibiotics, I just want to say that for antibiotics, you are using it to treat a bacterial infection, and if it is that is infecting your shrimp, there would be no sense in treating it with an antibiotic. In fact, you would just be throwing money away into the shrimp pond. And on top of that, if there are antibiotic residues that are found in your shrimp at harvest, there will be penalties for this. So I think it is better to have a proper diagnosis, as Dr. Kallaya has recommended. Have the PCR test done when there are moribund or diseased shrimp in your pond, and make sure you know what disease and problem you have in your stock before you embark on a treatment regime. And if I might add in, for most shrimp viruses, it's you wouldn't be able to treat a viral infection once it's in the stock. So the best policy you can have is actually just
prevention.
Your biosecurity. You prevent it from happening before it gets in. Okay.
You're right.
We have one more question here, again from anonymous, Dr. Kallaya. So the question is, how far down the food chain does DIV1 go? Will it be transmitted through fish oil products, and does this have any effect on humans?
Okay, I will start with the second question. Will it have any effect on human? I think from the all the shrimp virus infection, there is so far no reported to have any effect on human, and I don't think they have. Will it get transmitted through fish oil product? Again, as I said, I'm in Thailand and we don't have the DIV1 by now. So we don't want to have one. So I haven't tested if it's going to be transmitted through the fish oil product. I still don't know. But if anybody want to test it, and you are welcome to talk about it with our team, I mean.
I suppose, Dr. Kallaya, the concern about it being transmitted in fish oil would be if this oil is then used in producing feed for shrimp, and then fed back to shrimp, then there could be a risk pathway there for individual farmer. Yeah. So I think that's all the questions we have.
We can have a few more, but I think it's mainly a few questions to Luis.
Yes, we're just confirming this. So, yeah, so.
And this is additional information, so that's not a question.
Okay, so thank you very much, Dr. Kallaya. You have held this Q&A session by yourself because Luis is not here. And, yes, so I thank you very much for presenting during this talk, and also being very brave and sporting in taking the questions. We will now take a short break and go through some of the videos before our next session starts at 3 o'clock, where we will be joined by John Wigglesworth and Guillaume,
Myself.
yes, who is here with me in the room. And we'll be talking about seafood safety. So get a short break now for a few minutes. We'll see everyone in a bit.
Okay.
Singapore is a small urban nation with around 1% of our land set aside for agriculture. Where can we grow our food?
Wigglesworth.
In 2019, the Singapore Food Agency put forward an ambitious goal for sustainable food security in Singapore.
30 by 30.
30 by 30.
30 by 30.
Currently, less than 10% of our nutritional needs are produced locally. SFA aims to increase local production to meet 30% of Singapore's nutritional needs by 2030. Aquaculture is a pillar of Singapore's agri-food industry, striving towards this goal by employing climate-resilient, resource-efficient, and sustainable technologies. At the forefront of these innovations is a vibrant R&D ecosystem, comprising institutes of higher learning and research facilities, working to ensure the technology paves the way ahead for the aquaculture industry. The Singapore Food Agency has supported both land-based farms as well as coastal farms in a sea of ways, from co-funding R&D to supporting the adoption of new technology and future-ready solutions. By utilizing innovation, technology, and research to maximize efficiency and productivity in our offshore and land-based farms, we will be able to grow more with less and achieve our 30 by 30 goal, bringing Singaporeans a safe and secure supply of food for years to come.
And thank you. Now we are back. And thank you for staying after the first session. The second session will be on food safety. I'm Mr. Drillet. I will be introduced a bit later by Diana, and I would like to introduce our first speaker, with John Wigglesworth. And thanks, John, for being online so late. John, also early, two ways of looking at it. John will speak about ASC certification in seafood. He's a head of supply chain assurance for the Aquaculture Stewardship Council, and he has 32 years of experience in seafood production, sourcing of food safety, aquaculture production industry, and transition now in food importation, seafood importation. He is now sourcing food for Darden restaurants, international retail, club, and food services. John, I will let you go through your presentation now. Thank you.
Impacts on Food Safety and Human Health. Presentation to the World Aquaculture Society, December the 15th, 2020, John M. Wigglesworth. Hello, my name is John Wigglesworth, and I'm Head of Supply Chain Assurance for the Aquaculture Stewardship Council, known as the ASC. Today I'm going to talk to you about food safety topics in aquaculture, why they are important and areas of focus, and finally give you an insight into the ASC's perspective on the subject. This webinar will focus on the overall process associated with aquaculture farming and discuss each of the steps in the context of general concepts, site selection, feed supply, veterinary drugs, harvesting equipment, and supply chain custody. The aquaculture industry should operate to minimize the chances of food safety hazards during production, husbandry, and post-harvest handling. This is outlined in Codex Standard CAC RCP 522003, which offers advice on production, storage, and handling of fish and fishery products, but the same concepts apply to aquaculture. The code uses Hazard Analysis and Critical Control Point, HACCP, which is a science-based system that aims to prevent food safety problems from occurring rather than having to react to non-conformance of the finished product. The HACCP system accomplishes this by identification of specific hazards and the implementation of control measures. An effective HACCP system should reduce the reliance on traditional finished product testing. Its application to aquaculture should not be discounted, but rather embraced as a systems approach to assessing sites for selection, evaluating the physical environment for risk of contamination, and evaluating the inputs and outputs to avoid adverse effects to human health. Aquaculture products are at greatest risk from antibiotics, both approved and those used in improper management. High stocking densities in aquaculture increase the risk of pathogen transfer, which creates an incentive to utilize antibiotics. Contamination of fish with microbial pathogens of fecal origin can be more likely where facilities are close to human habitation or animal husbandry, so farm fish are likely to harbor these pathogens compared to wild fish. Every year, an estimated 48 million people, 1 in 6 Americans, suffer a foodborne illness. Of those, 128,000 are hospitalized and 3,000 die. Few of those illnesses are reported to the CDC. Fewer still are solved for both food source and contaminant. The produce category is the top category for outbreaks and illnesses, 643 outbreaks and 20,456 illnesses. Seafood, however, is responsible for the second most outbreaks, 542, but relatively few illnesses due to the small size of an average seafood outbreak, about 10 illnesses per outbreak. While outbreaks associated with USDA regulated foods include poultry, 372 outbreaks, 11,580 illnesses, beef, 249 outbreaks, 5,452 illnesses, and pork, 153 outbreaks and 4,001 illnesses. Pound for pound, fruit and fresh produce are among the safest foods to eat. However, seafood was assessed to be the most hazardous on a pound for pound basis. A consumer survey found that seafood is the category that concerns consumers the most. Contributing to consumer concerns, 85% of seafood is imported, and the FDA, which inspects only 1 to 2% of those imports, has identified numerous violations from drug residues to excessively high pathogen levels in certain products. The most widely consumed seafood product in the US is shrimp, which comes from large aquaculture farms overseas. In addition, a study found that seafood fraud has become more common, with an estimated 1/3 of seafood being mislabeled. Mislabeling leaves consumers in the dark about where their food comes from and what species they are consuming, which could have adverse health consequences, as demonstrated in 2007 when toxic pufferfish was mislabeled as monkfish. Provenance and food safety go hand in hand. The essential point to understand is that foodborne illness from aquaculture can be prevented through appropriate food safety measures. And while there is a certain degree of shared responsibility amongst government, regulatory, aquaculture, process and consumers, the aquaculture industry can institute farm management programs around HACCP and basic good husbandry practices in partnership with certification schemes that promote responsible management of aquaculture operations. The HACCP system offers a systematic approach to the identification and assessment of hazards, risks associated with production, processing, distribution of aquatic foods, and puts the responsibility to produce safe products firmly on the aquaculture sector. The principles of HACCP should form an integral part of the farm-to-table food safety continuum, thereby increasing consumer confidence in products from aquaculture and expanding market opportunities. Equally, aquaculture certification schemes have effectively reduced therapeutics such as antibiotics and chemicals by improving water quality and resulting in reduced farmed mortalities. Aquaculture facilities should embrace the principles of good aquaculture practice for the species they are farming, since it has a knock-on effect on husbandry, animal welfare, and ultimately product safety. Farms should be in areas where the risk of contamination by chemical or microbiological hazards is minimal, and where the sources of pollution can be controlled. Effluent should be treated appropriately for sediment and waste management to allow organic loads to reduce before discharge into the environment. Growing water should meet minimum standards that are suitable to produce products for human consumption. Farms should not be sited where there is a risk of contamination of the water in which the fish are reared, such as areas located close to animal husbandry or human habitation, which present challenges if there is the risk of fecal contamination into the watercourse. All chemicals, fertilizers, and additives should be applied with good agriculture practice in mind to avoid contamination of products destined for consumers. Aquaculture feeds represent a potential risk of contamination from chemical, mycotoxin, and pathogens. Feed should be stored appropriately at correct temperature and time parameters. Ingredients should not contain unsafe levels of pesticides, chemicals, microbial toxins, or other adulterating substances. Feed should be labeled correctly with formulations reflecting the standards regarding hygiene. Ingredients should meet statutory requirements for levels of pathogens, mycotoxins, herbicides, pesticides, and other contaminants that may give rise to human health hazards. Additives such as colors must meet legal requirements in the country of production and country of final sale. Feed that is compounded industrially or at the fish farm must contain only additives that are permitted by the competent authority in the country of production and in the country of sale. Veterinary drugs should be administered in accordance with recommended practices, comply with national regulations, and applied under veterinary supervision. Finally, and perhaps one of the most important components, is that there should be an appropriate system of ingredient and feed product tracing. Again, effective provenance is a key tool to creating safe aquaculture feeds and safe aquaculture products. An estimated 70% of farmed aquatic species are dependent on feed to complete their production cycle, and feed constitutes the greatest single input in terms of costs. Thus, feed represents a major component of the environmental and social footprint of aquaculture, and it's important to define precisely what constitutes responsible and sustainable aquaculture feed production. Considering environmental and social footprints, feeds are important since aquaculture is the fastest growing animal production sector in the world and is forecast by the UN Food and Agricultural Organization to provide 2/3 of seafood destined for human production by 2030. Feeds are subject to the same supply chain risk as finished product itself: contamination, poor processing, and poor storage. This data is a compilation of the official refusal statistics for shrimp from the USA, EU, and Japan. The data serves to illustrate that although antibiotic use is reported to be getting less due to more biosecurity and improved husbandry practices, antibacterial therapy remains the last option to combat bacterial infections in aquaculture, and this is reflected in import refusals. The presence of India at number 2 was also reflected when India faced an EU ban for antibiotic presence in August of 2017. In November of the same year, a second report evaluating controls in place for fishery products from India concluded that while the controls in place for the fishery system are capable of providing adequate assurance, the official controls do not apply to domestic production, and as such the sharing of water resource between export farms and those for domestic production resulted in cross-contamination through the water supply. Aquaculture uses a combination of formulated feeds, antibiotics, chemicals, soil and water treatments, pesticides, fertilizers, prebiotics, and probiotics. However, antibiotics are some of the treatments that are most frequently used and come from compounds from synthetic and natural origins that kill or impede the growth of aquatic pathogens. However, They are also applied as growth promoters and preventative treatments. So what constitutes the common therapies employed? A review of antibiotics from the top 15 producing countries, 50 published papers representing the bulk of worldwide literature. The review reported 67 antibiotic compounds were used in aquaculture from 11 of 15 major producing countries between 2008 and 2018. 73% used oxytetracycline, sulfadiazine and fluorphenicol, and 55% used sulfadimethoxine, erythromycin, amoxicillin and enrofloxacin. On average, producers used 15 antibiotics, but Vietnam and China used 39 and 33 antibiotics respectively. While there is a shift toward the restriction of banned antibiotics such as nitrofurans and chloramphenicol, and those deemed by the WHO as critically important for human medicine, penicillins, quinolones, chloramphenicol and nitrofurans are still found regularly in aquaculture products. What is the implication of antibiotic misuse to human health? Adverse drug reactions occur when an individual develops antibiotic sensitivity with a knock-on effect to human treatment options for disease. Antibiotic sensitivity causes diarrhea, nausea, vomiting, rashes, and gastrointestinal distress. Such adverse reactions are immune system mediated, impacting various organ systems. Some antibiotics such as tetracyclines, sulfonamides, and penicillin are antigenic and can contribute to allergenic symptoms. Chloramphenicol increases the risk of subject developing aplastic anemia and agranulocytosis by lowering white blood cell count. The occurrence of antibiotic resistance, ARB, and antibiotic resistant genes, ARG, is another way that antibiotics create a public health risk because antibiotic resistance can transfer from the aquatic organisms to humans. The fish pathogens and other aquatic bacteria exposure to antibiotics can develop ARGs through various mechanisms. This is transferred to humans indirectly via bacterial plasmids and directly via zoonotic pathogens such as Aeromonas or Vibrio. Alteration of normal gut flora results in an increased number of infections from pathogens that are resistant to antibiotics, resulting in increased treatment failure and more severe infection. So what is the ASC position on antibiotic use? Within the ASC standards, no antibiotics on the WHO list of critically important antimicrobials for human medicine can be used. Antibiotics administered on the ASC salmon and tilapia farm must be prescribed by a veterinary practitioner as part of an agreed treatment plan. However, the ASC has measures in place for all of its aquaculture farm standards. Should the farmer use antibiotics or medicated feed for shrimp health and welfare, the ASC shrimp standard allows for some level of antibiotic to be used, but the treated shrimp will not be authorized to be sold as ASC certified, and those shrimp products are thus not allowed to carry the ASC label. If the ASC becomes aware that a labeled shrimp product tests positive for antibiotics, a thorough investigation will be undertaken to determine where and how the product encountered the antibiotic. Harvesting of farm fish and crustaceans and other aquatic products must be conducted in a manner that minimizes the potential from chemical or microbiological hazards. After harvest, the fish must be held, packed and transported under conditions that further minimize the potential for contamination. Appropriate time and temperature control are essential to minimize proliferation of microbial pathogens and spoilage organisms. Essentially, seafood must be treated according to 3 rules: wash it often, keep it cold, and move it quickly. Seines, nets, and traps used for harvest should be carefully selected to ensure minimal damage during harvesting. Harvesting areas and all equipment for harvesting, catching, sorting, grading, conveying, and transporting of live products should be designed for rapid and efficient handling without causing mechanical damage. Equipment should be easily cleanable and free from contamination. Conveying equipment for live and slaughtered products should be constructed of suitable corrosion-resistant material that does not transmit toxic substances and should not cause any damage or injuries. Surfaces in the handling areas should be non-toxic, smooth, impervious, and in sound condition to minimize the buildup of processing waste and increase the risk of microbial contamination. Adequate facilities must be provided for the handling and washing of aquaculture products, and they must have adequate supply of cold, potable water. Adequate facilities must be provided for washing and disinfection of equipment. Containers for processing waste material must be clearly identified, suitably constructed, sealable and made of impervious material. Separate and adequate facilities must be provided to prevent contamination of products and dry materials such as packaging, harmful substances, offal and waste materials. Hand washing and toilet facilities must be available and isolated from the fish and shellfish handling areas, and there must be an appropriate pest management system implemented to avoid cross-contamination. With complex international supply chains for many seafood products, substitution and mislabeling of seafood is a globally recognized issue. The ASC Chain of Custody Standard is a traceability and segregation standard that is applicable to the full supply chain, from certified farm to the product carrying the ASC logo. Each company in the supply chain handling or selling an ASC certified product must have a valid chain of custody certificate. This assures consumers and seafood buyers that the ASC labeled products come from a certified responsible farm. We use the Marine Stewardship Council MSC Chain of Custody COC standard to verify the origin of seafood sold as ASC certified. While the COC cannot guarantee a perfect supply chain, it does serve to support food safety because of the rigor in the provenance and program assurance resources. Food safety in the aquaculture industry starts at the hatchery, works through the farm, impacts the feed supply, and is part of the handling process through processing and shipment of finished goods. It must involve site selection, feed inputs, husbandry, harvesting, and processing to be comprehensively effective. Food safety must always involve a systems approach, such as HACCP, in addition to formal certification schemes represented by schemes such as ASC standards, which provide structure to develop food safety in aquaculture. Traceability and an understanding of provenance of origin are paramount in underwriting any food safety system, and systems underwriting provenance should always be challenged to ensure they work. Feed standards. The ASC feed standard defines requirements for factory practices and parameters for responsibly sourced ingredients. The standard is a tool that recognizes and rewards responsible aquaculture feed supply and applies to all standards. It provides an additional mechanism for producers and retailers to mitigate environmental and social impacts through their feed supply chain. Site standards. ASC standards set requirements for farming to guide seafood producers in minimizing key environmental and social impacts of aquaculture. The standard covers 11 farmed groups and are based on sound science applicable to different locations, types, and scale of operations. The standards cover biodiversity, feed, pollution, disease, antibiotics, and social issues. The ASC is acutely aware of the necessity for traceability through the aquaculture production supply chain, and its traceability and segregation standard is applicable to the full supply chain from a certified farm to the product carrying the ASC logo. Each company in the supply chain handling or selling an ASC certified product must have a valid chain of custody certificate. In this way, while the ASC cannot assure fraud will never happen, the ASC does have a mechanism to formally intervene and act. In this way, the ASC logo supports credible supply chain assurance to consumers. Thank you for taking the time to listen to my webinar.
Thank you very much, John, for your presentation. A lot of information. We have a couple of questions that already came in that we have already published on our Q&A section here. And for those who are watching us, please feel free to ask any question for John, since he's up in the middle of the night to answer all the questions. So John, I will start with the first one that we have. And the first question we have is the following. Are there any risk of antimicrobial resistance when used in aquaculture, when used often in aquaculture?
I'm sorry, could you repeat the question again?
Are there any risk of antimicrobial resistance when we use too much antibiotics in aquaculture, when we have regular use of antibiotics by the farmers?
I think the issue is, well, to answer the question, yes. You're always going to run the risk of antimicrobial resistance. The issue is always going to be if you're going to use antimicrobials, they have to be used in a fashion that is under the control of a veterinary health or an aquaculture health expert. Like most treatments, even treatments for human disease, if the dose response is not appropriate, then what will happen is that there's a greater potential for resistance to develop. You know, a good example of this is when somebody goes to see the doctor and they're prescribed antibiotics, and they don't take the full course of the antibiotics. They feel better after a few days, stop taking the antibiotics, and those are the conditions that lead to resistance. The same sorts of things can occur in aquaculture, and depending on the species being treated, I think there's a greater propensity for things like shrimp to essentially not necessarily get a correct dose of antibiotics versus something like a fish that will probably eat a pellet whole and get an effective dose. So yes, there is the risk of antibiotic resistance, and it has to be managed in the correct way with a veterinary health professional.
Okay, so that links back to our next question, John. We have a question from someone asking, how can we convince a farmer to use less antimicrobials? So that's a related question. So if you say we have to work through veterinaries, maybe there is also another way to basically maybe manage better the risk of pathogens. How do we work with farmers to make sure that we are using less antimicrobials?
Well, in all the years that I've been involved in seafood, it's always the $65 million question. How do you basically turn around to a farmer and say, look, it's a lot more worthwhile to produce a product that is not going to affect the supply chain, because ultimately that's what happens. It's not necessarily the farmer that sees the impact of an import detention. It's a supply chain for a country. Well, immediately it's usually the importer, and then it's the factory, and then it's the farmer. My own personal opinion is that the best way or the best mechanisms to work with farmers are with the processor that has, or the feed manufacturer that has a sort of a technical outreach group that promotes responsible aquaculture with the actual farmer themselves. And this also leads into sort of independent standards where the farmer themselves see an advantage, whether it be through the ASC or whether it be through a different standard, Global GAP or the GAA or whomsoever. When the farmer believes that they have something to gain by differentiating their product, and that would also include sort of non-application or reduced application of antimicrobials, then I think there is the benefit to sell an idea of less antimicrobials as a better way of selling a marketable product.
Thank you very much, John. And there are, I'm sure, a lot of linkage with the farming process and the place where the farming takes place, because there may be a pollution or chemical product in the food, the fish produced from the farm, but maybe not only from the farm. So we have the following question here, which is, can you tell us a little bit more about the site selection process and how to assess the risk for food safety as well as to the environment? So
yeah,
site selection, yeah.
It's something that actually I learnt probably an awful lot more about in the fresh produce industry, where you're primarily dealing with leafy greens which don't undergo a kill step by cooking. The aquaculture industry is a more challenging environment in which to say these are the parameters to say, I'm going to site my particular farm in this region. That's number one. Number two, there's also an awful lot of aquaculture facilities that are already been sited. Having said that, what would I identify as important components? Proximity to major conurbations where there isn't a treatment of human waste or even animal waste. I remember a situation in a factory that I ran down in Honduras where water was coming in from a deep well, and that was being basically utilized to process product within the factory. Well, during the rainy season, what would happen is that all the agricultural land would get a lot of water. It would compress basically agricultural feces through the water, through the soil, and the factory would end up with very high fecal coliforms, which created other problems within the factory. So while you can't necessarily turn around to a farmer and say, go and resite your farm if you're in, let's say, an area in the Mekong Delta, or if you're in a facility that's located downstream of a conurbation that doesn't have, exceptionally good processing of effluents. I think it's always worthwhile for a farm to be aware as to what they're going to encounter, and equally the factories that then receive that product, for them to be aware as to some of the challenges that they're going to face on raw material that enters the facility when it comes down to primarily fecal coliforms, the salmonellas, the shigellas, and the E. coli's.
Thank you, John. And we still have a bit of time and quite a couple of questions coming in. So I'm going to try to synthesize at least one or two of them. Okay. We have one question about whether the ASC feed standard have been issued or whether they are developed, and whether ASC certification covers as well SPF in shrimp hatchery.
The feed standard is it's still in development. It should have actually been released, but the ASC takes an approach of putting it out for public consultation, and those comments are being addressed at the current time. The next estimated time for the release of the feed standard, I believe, is going to be in the first quarter of 2021. So that is underway. It's been written, but it's under amendment per public comment. And what was the second question regarding hatcheries?
Yeah, whether you have a specific pathogen-free shrimp hatchery, whether ASC is covering those.
No, we don't. We haven't moved into the hatchery phase of things, and certainly not relative to a specific pathogen-free certification.
Okay, last one, since we still have 1 minute. John, how about, or how far traceability and quality control certificate can avoid frauds in seafood or in seafood trade?
Well, no system will ever avoid fraud. The challenge is always to have in place a mechanism to investigate it. So there are systems out there that have a mechanism of chain of custody. One of them is the ASC. I believe the other one is the global gap. What the chain of custody essentially allows you to do is that when something occurs, perhaps in Europe, perhaps in the US, perhaps in Asia, where antibiotics have been detected, then there is a formal process to investigate through the supply chain as to where that's actually occurred. So what a chain of custody essentially does is it gives you the mechanism and the tools to really get to the bottom as to where the problem resides and to take actions accordingly. If it's a traceability system of one up and one down, that doesn't necessarily support a full supply chain? So I would say I would answer the question by saying the more you understand about your entire supply chain, the better opportunities you've got to investigate fraud. And if you can investigate fraud effectively, then you have the opportunity as to where you can try to resolve it.
Thank you very much, John. And I think we have burned all the time that we had allocated for this presentation on food safety. John, thank you very much again for being with us in the middle of the night. With that said, I will hand it over to Diana next to me, since she has to introduce me for the next presentation. Thank you very much.
Thank you very much.
John. So we now move on to our second speaker for this session, who is Guillaume Drillet. Guillaume currently holds the role of the Regional Manager for EHS Marine Services at SGS that supports private and public organizations with their research, oil compliance, sampling, testing, and monitoring. Guillaume has 19 years of experience working with environmental scientists in the public and private sectors. And after 3 successful years as President of the WA2020 Chapter, Guillaume has been elected Director of the Board of the World Aquaculture Society, where he chairs the Industry Committee and the Subcommittee on Social Media. So while running the business development for the marine services of SGS in Asia and the Pacific regions, Guillaume continues to deliver lectures in academia and to global organizations such as IMO. So now over to you, Guillaume. Presentation.
Good morning, good afternoon, and good evening. Thank you for joining this webinar. I'm Mr. Drillet, and it's my pleasure to introduce this presentation on plastic in aquaculture. As you may notice, there are 4 presenters listed here, and I owe you an explanation for this. In the last couple of months, I had the chance to chair a series of roundtables in the topic of plastic in aquaculture, and we have had experts from 21 different organizations participating. I want to thank all of them. They represented a large range of stakeholders, farmers, scientists, feed and additive manufacturers, commercial laboratories, and so on. This roundtable online came in because of the urgency to deal with this topic within our field. There are gaps of knowledge. The reporting of information on this particular topic most of the time mixes aquaculture and fisheries, which may not be appropriate. And the aquaculture industry, while not necessarily being a large polluting industry in that respect, is definitely one of the industries that will be the most highly impacted by the presence, at least, of micro and nanoplastic in the water. We had initially planned to have a special session last June. We will need to wait until next June because of the actual situation, and I'm looking forward to see all of you in June in Singapore. Until then, we had decided together with IMRS, and we had agreed to organize these roundtables. There will be a report produced in the West magazine in December, also published by IMRS, so keep an eye for it. Until then, I would like to welcome 3 of our experts to introduce the main information that was discussed during the successive event. Kirsten, the floor is yours.
Thank you very much, Mr. Drillet, and good morning, afternoon, and evening, colleagues. My name is Kirsten Gilardi. I'm based at the University of California, Davis in the United States, where I run the Wildlife Health Center at the School of Veterinary Medicine. I also run the California Lost Fishing Gear Recovery Project, which works with commercial fishermen to locate and remove abandoned, lost, and discarded fishing gear from California's coastal ocean. Thank you for the opportunity to participate in this session and to share with you some of the work currently underway worldwide to better understand ocean-based sources of plastic. It's been my honor over the last 18 months to chair a new working group of the Joint Group of Experts on the Scientific Aspects of Marine Environmental Protection, or GESOMP. This working group has been focused on sea-based sources of marine litter and was established at the request of the International Maritime Organization, the Food and Agriculture Organization, and the UN Environment Program. We're comprised of the 12 individuals listed at the bottom of this slide, all scientific experts in both ocean-based industries and marine debris. I'd like to take a moment to acknowledge their tremendous contributions to the work undertaken over the last several months. As we speak, we're putting the finishing touches on our final technical report, which will be submitted for peer review shortly. And we anticipate the report will be released sometime in early 2021. Next slide, please. Guillaume Working Group 43's charge has been to conduct a comprehensive review of the state of knowledge around sources of marine litter from ocean uses. And by litter, we're primarily focused on plastics. Of course, our audience today is well aware of the great momentum worldwide to address the issue of ocean plastic pollution, and there's been a lot of focus on land as the source of plastic marine debris. But there's also a need to better understand how much ocean-based industries like fishing and shipping and oil and gas development and aquaculture may be contributing to the global burden. Working Group 43's charge is to establish a state of knowledge on this topic and to estimate quantities and examine impacts of ocean-based sources of marine litter on marine life and habitats. We've been particularly focused on shipping and fishing as sources. ALDFG stands for abandoned, lost, and otherwise discarded fishing gear. But Working Group 43 is also examining what we know about coastal and marine aquaculture as a source of marine plastic litter. Next slide, please. The aquaculture industry has been very interested and proactive to date in better understanding if and how aquaculture is contributing to the global ocean plastic burden, and the work of Working Group 43 has really benefited from these efforts. For example, the FAO conducted a large study of the use of plastics in fisheries and aquaculture in 2017 and identified aquaculture operations that depend on the use of gear comprised in part of plastic, especially expanded polystyrene floats and netting and boxes. In particular, a report produced by the Aquaculture Stewardship Council last year thoroughly reviewed the use of plastic to construct aquaculture equipment, and it really should be considered the definitive document on that subject. Another Guillaume Working Group 40, has been engaged for the last several years on better understanding all sources of microplastics in the ocean and has issued several reports that are available on the Guillaume website. And as well, there have been many excellent papers published in the peer-reviewed scientific literature examining the occurrence and quantities and impacts of plastic debris in the ocean resulting from coastal and marine aquaculture operations. The majority of that research has been taking place in the Mediterranean, South Korea, and Chile. Next slide, please. I think it's also important to make the audience aware of some important global initiatives underway that the aquaculture industry has much to offer in terms of helping those initiatives achieve goals for reduction of the global ocean plastic burden. These initiatives largely stem from the Honolulu Strategy, which arose out of the 5th International Marine Debris Conference held in 2011. The strategy serves as a framework for the reduction of the ecological, human health, and economic impacts of marine debris worldwide. UNEP has since established a global partnership on marine litter, and FAO and IMO have recently launched a joint global litter partnerships program as well. Note that marine litter will be addressed at FAO's COFI meeting in February 2021. Information about all of these initiatives is readily available on the web. I'd also like to bring to your attention some important non-global initiatives. In particular, the Global Ghost Year Initiative has succeeded in bringing many nations, governments, non-governmental organizations, and industries together to collaboratively address the problem of abandoned, lost, and otherwise discarded fishing gear. I encourage you to visit their website to learn more about the GGI. Thank you for your attention, and now I'll turn it over to my colleague, Belinda Yashley.
Managing plastics at the farm level is thinking about macroplastics. Currently, there is an abundance of plastic that ends up in our oceans due to aquaculture. And this is because a significant portion of equipment is comprised of plastic. For example, nets, rope, and pipes are the main offenders. There's a significant portion of this equipment as explained. And the plastic waste from aquaculture results from normal wear and tear, from accidents, such as catastrophic losses to do with extreme weather events, improper management, and a key here is a strong maintenance program. So where there exists poor maintenance systems, there is often an issue with marine debris. Currently, there's no global estimates for the amount of plastic generated by the aquaculture sector, but there's some various estimated volumes from the European Economic Area, 41,000 tonnes lost annually. The Norwegian aquaculture suggests 12,300 tonnes of plastic waste was generated in 2011, and in South Korea they're considerably more, 39,700 tonnes in 1999. But as you can see, these references are quite old, with the exception of the European economic volumes coming from a 2016 paper. There is, however, currently and more recently one sector that's certainly making strong advances towards managing plastics on farms, which is the Tasmanian salmon industry, and I'll give some examples there of the approach. So the first step for the aquaculture facility, and this has been the approach for the Tasmanian salmon industry, is to make the commitment to manage ocean plastics. This commitment looks like, is in the form of a company policy which specifically addresses the management of plastics. So it's getting the entire business on board to commit to putting systems in place. The key here is the housekeeping, so having plans and procedures in place. A key plan is a waste management plan at the farm level, which identifies the types of materials that are used on the farm that contain plastics and how to manage them. This plan is supported by procedures, and these procedures include provisions for mitigating risk of release of these plastics and this equipment into the water. Also supporting the plan is building a plastic register to map the use and needs of types of plastics in operations. Very often there's an underestimation, and the risk register, the plastic register, helps identify this and the amount of plastic used at the farm. And developing a register has many advantages. It can help manage plastic over the lifetime of the equipment. It allows for planning for recycling and to manage mitigation measures, so the loss of gear. There's really three levels from prevention to response. Written procedures and plans when they're in place. So with those plans, the supporting systems and procedures, there can be adequate prevention and a plan to respond if required. Although the key focus here is preventing plastics from leaving the farm, so prevention really is the key. And one of the most effective ways to prevent plastic as marine debris is education. So training of staff is paramount here, so that the staff understand clearly the impacts of marine debris and where in the staff's daily activities and role they can play a part in prevention of plastics becoming lost or becoming loose. So the staff really should understand their role in marine stewardship, and this cannot be emphasised enough in the battle of ocean plastics and aquaculture. So the key areas here are a plastic register at the farm level, the register and ID of infrastructure on or in the water, waste management plans, and then looking at procedures that support that, such as strength testing as standard operating procedures for net and for rope. So making sure the gear is well maintained and there's a maintenance program in place and a risk management plan. So with all of this in place, and adequate training of staff, the Tasmanian salmon industry has been able to reduce the plastics substantially.
Thank you, Belinda, for this very nice presentation and example from Tasmania. We'll let now Natalie to talk about nanoplastic and microplastic reaching the farm.
It should be clear to you all at this point that plastics are found throughout the aquatic environment. And while a proportion certainly arise from activities in fresh and saltwater systems, including as a result of aquaculture, the evidence consistently indicates that the largest proportion of plastic debris comes from the terrestrial environment. We may think in the same terms when considering micro and nanoplastics. For example, it is believed that the majority of synthetic fibres will be released to aquatic systems via wastewater treatment and not from the fragmentation of fishing gear, pens and other ropes and lines. Nevertheless, proximity to certain plastic sources increases the chances of any individual, fish or invertebrate, interacting with or ingesting micro and nanoplastics of that type. In the same way that I must be aware of and exclude micro and nanoplastics from clothing and cleaning cloths in airborne lab samples due to the prevalence in the environment which I work, so too might you see a greater likelihood of micro and nanoplastics from things like pens, feed sacks, and the feed itself. Whether sourced from terrestrial systems, other aquatic industries, or your own facilities, we must be aware that micro and nanoplastics are readily taken up by a range of species. However, the amount that we see may be influenced by a number of different factors. Key amongst these are the level of environmental contamination and the characteristics of the plastic material. It's hard to consume plastics that are larger than the food that you are able to readily ingest, and it's easy to excrete plastics which are small enough to easily pass through your digestive tract. Retention of plastic by an animal is also variable, changing in relation to the length of time plastics may be held in either the gut or the tissues. This is influenced by the size of the plastic, with nanoplastics more able to cross the gut wall and into the tissues, or with the complexity of the animal's guts, with complex structures more likely to hold on to plastics. For example, the image on screen is of a bolus of plastic fibres held in the stomach of a langoustine, unable to pass through the gastric mill and on into the hindgut. As a result, the implications of both microplastic and nanoplastic exposure can vary between species. The impacts of said exposure on the animal may be negligible, as has been reported in a number of studies, but other studies have seen effects such as reduction in growth, changes in behaviour and alteration in morphology and histology. The fact is that the current depth of research is insufficient to draw concrete conclusions which will be relevant across the industry. However, this is neither a reason to be less vigilant, nor is it sufficient to assuage the concerns of some consumers. In light of these issues, it was the conclusion of our group that the industry must take the lead in monitoring and limiting microplastics and nanoplastics in aquaculture systems. And in our report, we highlight a number of questions that may be of interest to the industry, including where might microplastic contamination come from and how microplastic uptake might be measured. And we identify widely used, simple and globally applicable protocols that are considered suitable to answer these questions. For example, the table on screen highlights measures for monitoring of plastics in an aquaculture setting. Of particular interest here are microplastics, whose monitoring requires less costly methods than those of nanoplastics and may be more accessible by most producers. It is hoped that by determining contamination levels and identifying the origins of microplastics, facilities may not only reduce their own microplastic and nanoplastic footprint, but also be able to highlight where they are unduly affected by the activities of other potential plastic sources. It has already been indicated that aquaculture is not the greatest source of plastic debris of any size, and it is important to recognise that micro and nanoplastics have been observed in a range of consumables, including kitchen salt, beer and bottled waters. However, the persistent media and public focus on marine plastic pollution has kept the discussion centred on fish and shellfish, and there may be a disproportionate effect on consumer confidence as a result, despite there being currently little to no evidence on the effects of plastic on both food safety or human health. Again, by taking ownership of the issue and by encouraging other food and drinks producers to do the same, the aquaculture industry can take control of the quality of the product, reassure customers and consumers with regard to food safety and the sustainability of the industry, and have a more impactful voice in the discussion of public policy surrounding the plastic pollution issue. For a more in-depth look at our discussion and recommendations, please do take it our report when it's published. All that remains for me to do now is to thank Guillaume for keeping us organised throughout this process, my fellow presenters and report contributors, and you, the audience, for your time. I will hand you back to Guillaume for questions. Thank you so much.
Thank you very much, Natalie, for closing the presentation. And yes, it's a presentation with many presenters because it's basically the results of a long work, as I said, from 21 different organizations. We have received a couple of questions, and if you have more in the next couple of minutes, please feel free to submit them. The first question I will start with is actually the second one we received, and it's how can we measure the level of microplastic accumulated in cultured food fish, and what kind of health concern will arise when consuming microplastics through food? I will try to basically respond with the general consensus that we had in the discussion. In general, we need to start discussing about what do we call microplastic, because there are two schools for this. One school considers that microplastic starts at 1 micrometer to 5 micrometer. Another schools consider that we should look at microplastic starting from 0.1 micron, because under that nanoplastic can go through the gut membrane and therefore accumulate in the food we eat and not just in the gut. There are impact raised for a couple of species on the content of plastic in the gut, because even though it may not directly affect the organism by physiologically, it may still impact, for example, digestion and so on. What are the health concerns? There is still a lot of unknown here, and this is one of the biggest issue, not to pinpoint at aquaculture as an industry producing feed containing plastic, considering that actually we are drinking from plastic bottles, we buy milk in plastic bottles and so on. And we find particles of microplastic, as Natalie was saying in the last part of the presentation, in a lot of different food products that we eat or drink on a daily basis. And that's just to give an overview of what this group have been discussing about. And we had very, very long and very pertinent question on this. If you want to have further detail, we have the report published on the WAS website. It was put online today, so feel free to have a look at that. The first question from Royal Bosma is actually a very pertinent question, and this is also something that we have been discussing for a very long time. In this roundtable and in previous roundtable that we had been running, for example, for shipping together with IMAREST, the problem of plastic is actually what do you do with the plastic you accumulate in a farm or on a ship or wherever you are. You need to be able to recycle it, and to be able to recycle it, you need to have station or governmental area where you can go with your waste, or the government should pick up the waste that you found, so that plastic can be managed for the end of its life. You can recycle plastic. We have a big challenge though in aquaculture, because a lot of the nets and so may be full of biofouling, and so some of these recycling, existing recycling factories may reject the plastic. What do we do with it then? And that is really a big question. So the question is not just an aquaculture question, it's a question of what are the government going to do in order to ensure that we can manage plastic through its entire life cycle. And if you remember at the beginning of the presentation, we mentioned that 80 or 90% of the plastic we find in aquatic environment is actually coming from terrestrial habitat. So it's coming from dumping areas, flushed down to the sea from the rivers, and it's not necessarily, I would say, due to aquaculture. So the aquaculture sector is far from being the first polluter when it comes to plastic. Doesn't mean that we should not do anything. This is what ASC has started working on. This is what Belinda was introducing in our presentation, that Tasmanian salmon farmers already started marking the gears and have plans for what to do when they lose the gears and so on. So there are actually some things moving in our field, and I think we will eventually get better, but it's time to start somewhere. Now we have another comment from Royal, but I'm not sure what it is about. Do you know? The microbeads?
Yeah.
So we have a question from Royal Bosma, but I'm not sure what the microbeads mobile application is when buying cosmetics, soap, and food, and so on. I have no idea what this is. So we are not using it yet, or at least I'm not. I don't see any additional questions so far. All right. So it's an application where we can find whether we have plastic in the cosmetics and food. Now, we have had a very long discussion about what to test for and how to test. Today, there are no official international standards for sampling and for analyzing. And we concluded that it was actually not necessarily very bad, because we are still at the research phase in many respects in this area of plastic. But in order to be able to widespread testing, sampling, monitoring, we need to be able to start with something relatively standardized. And this is why we propose an example in this report, where we say, why not we start with this list of testing and testing scheme for everyone. There's still a lot to develop. I do believe when we know what we are looking for, when we are capable of targeting some, I would say, area or some size of plastic in some environment and so on, we will be able to have international standards. And from that moment, it will be much easier for laboratories to start implementing that as a routine testing. There are no new question for now, and therefore I think we should. Oh, there may be one more. Wait a sec. So we have one more, which I will publish now, so every one of you can see it. Is there any evidence of micro or nanoplastic impacting aquaculture production, or an indication of how we might come across this plastic presence increase? For example, should we expect bivalve to show significant impact first? Yes, I think most of the report that have been published today, and if you look at the FAO report from 2017 or 18, in every single portion of mussels or bivalve that you will eat, you will find some level of microplastic, because they are filter feeders, so there is a relatively high potential impact. But it also depends where your farm is placed. So site selection may include, for example, evaluating whether they are microplastic. And because nanoplastic is very difficult to measure, as a shortcut for now, until scientists have discovered much more about that topic, you could consider that when you see microplastic, there must be some nanoplastic as well. But that's a very heavy shortcut, so we have to be slightly careful on this. I think the working group that we have started here will continue working together toward the meeting in June. So if people have interesting set of data, they are more than welcome to submit an abstract to the conference, so we can have a great session in June. And if you have any further question, I'm happy to put you in touch with the expert that we had in the working group. On that conclusion, I think we can close the meeting for today.
Yeah.
And I would like to thank all of you for staying online with us so long. Sorry again for the slight challenges on the presentation early in the presentation. I would like to thank all the panelists. thank you very much, John, for joining us online so late. I'm sure ASC will look into those plastic with even more, how could I say?
Greater focus.
More focus.
It could be the next thing, because it looks like AMR is the big issue this year, probably in the coming years. There's a lot of traction that's going on for antimicrobial resistance. So much concern about the use of antibiotics in food animals and in aquaculture. But I mean, I think the narrative that is running through the session for me is that with aquaculture, you produce something in the environment, so you are affected by all the inputs to that environment. And we have to pay attention to what we add to the environment so that what the product that comes out is safe for people. Yeah.
Thank you, Diana.
Yeah, sorry, I will stop now.
Thank you. Thank you, everyone. And we are looking forward to have you online tomorrow for our next session. Goodbye.